Hi everyone, I'm Yanxuan. I'm a second-year PhD student at Melbourne Uni. I'm supervised by Joe Brown, Russell from Melbourne Uni, and Laurie from UNSW. And so today, the topic of this talk is actually from my first year PhD research that I just submitted like 2 weeks ago. It is about investigating the impacts of an AMOC slowdown on Australian climate at 8.2 thousand years ago using the ACCESS-ESM1.5 model. And in the end of this talk, I will also show some of the preliminary results from my current runs, which I've been using quite a lot of KSUs from the ACCESS-NRI. But since that experiment, that simulation is still at early stages, so I thought I may just present this first. The Greenland ice cores recorded an abrupt cooling of 3.3 degrees Celsius over Greenland that lasted for around 150 years, which is the largest abrupt cooling event in the Holocene period. So here we see the Holocene starts roughly 12,000 years ago, and the 8.2 Ka event is here. On the right-hand side, here shows the oxygen isotope ratios for the 8.2 Ka event with different locations over Greenland in different colors. And, all of them indicate an abrupt decrease in temperature. And this bottom panel here, basically you can see from the outer dashed lines indicate the onset and the termination of the whole event. And the inner dashed line indicate the period of central event with peak cooling. So what actually caused the abrupt cooling? The original hypothesis is the proglacial Lake Agassiz drainage theory. So the dashed line here indicate the Laurentide ice sheet during early Holocene. The shaded area here is the proglacial Lake Agassiz. So the meltwater during deglaciation just keep draining into the lake until ultimately there was a catastrophic outburst into the Labrador Sea via this Hudson Strait through this route B. And this results in a weakened AMOC and cooler temperatures around the North Atlantic regions. And on the right here, the first panel is the same, the Greenland temperature record from Greenland ice cores. And these ones are the North Atlantic seawater oxygen isotope records for different locations around the Labrador Sea. So basically we can see a decrease after the event. So basically indicating a weakened AMOC. And if you look at the thick blue line here, which is located around here in the south of Labrador Sea, and the purple line here is around here. And these two lines show a larger decrease in the oxygen record, isotope records, potentially indicating the freshwater transport pathways is through this way. So some later studies have proposed that the 8.2 Ka event was not solely caused by a lake outburst, but also due to a combination effect of accelerated ice melting and the lake drainage. So basically, like similar to the proxy records in the first slide, there's like a two-phase of the event with peak cooling, which may be caused by the lake outburst, and then during the full event of 150 years with the background forcing from the deglaciation. And the estimated total sea level rise is about 0.8 to 2.2 for the whole event. So here shows some proxy records for the 8.2 Ka event. C and D here are the inferred precipitation and temperature anomalies during the 8.2 compared to the early Holocene from Memorial 2013. So basically, the proxies indicate drier conditions over Greenland, Asia, Southern Europe, Northern South America, and parts of Southern Africa during 8.2, and some suggesting a strengthened Asian winter monsoon and enhanced precipitation in the Southern Hemisphere and tropics region, suggesting a southward shift of the ACCESS. And A and B here are the split-zone records from Parker and Harrison 2022. So despite there may be some differences like in the interpretation between the two studies, in some regions, we can see the proxy records are concentrated over the Northern Hemisphere, fewer over the Southern Hemisphere, and we know absolutely nothing about the climate in Australia during that time. So the aim of this research is to investigate the climate response over Australia and performing freshwater hosting experiments under the 8.2 Ka climate conditions. So the first thing is just setting up the background state. So we only change the orbital parameters and the greenhouse gas concentrations. All the other forcings remain the same as pre-industrial. And here we see the monthly incoming shortwave radiation at top of atmosphere at 8.5 Ka compared to pre-industrial. So basically we can see increased seasonality in the Northern Hemisphere and decrease in the Southern Hemisphere. And so actually we performed another simulation of the early Holocene at 9 Ka with 300 model years of run. And so we basically initiate this study, this simulation from 9 Ka, and we run for 50 years to equilibrate the small changes from 9 Ka to 8.5. And then at model year 50, we added freshwater forcing, the background freshwater forcing of 0.05 spherural into the Labrador Sea, this yellow box here, to simulate a small and continuous flux of meltwater from the Laurentide ice sheet prior to the lake outburst. And this is also following the Piemann protocols. So after 200 years of the control, and so we introduced that there were two types of hypotheses for the cause of this event. So we also included two types. So the first ones are the short duration poles. I put one schedule for 1 year, one for 5 years, and so forth. We also include one of the same as one schedule for 5 years, but started 6 model years later at a higher initial AMOC strength to see the difference in the AMOC and the climate response. And we also include a time varying long-term freshwater hosting experiments to basically simulate the lake plus ice collapse hypothesis. And after the hosting, we continue the runs to monitor the AMOC recovery with the background fluxes applied, same as the 0.05. So here we have the AMOC and sea surface air temperature response over the Atlantic Ocean, and the shaded area is indicating the 2 standard deviation. It's pretty obvious as only the long run, the time varying long run experiments keep the AMOC weakened significantly for more than 160 years, as suggested in the proxy records. And the North Atlantic surface air temperature decreased significantly in this blue 1 schedule 5 years and the 1 schedule 5 years, but 6 model years later, and this green line here. And however, only the weakening in this green line is large enough to result in a significant warming in the South Atlantic. And the two Wandsworth 5-year experiments show similar response in this one, but the purple line has a much smaller amplitude of temperature decrease, although the AMOC response is quite similar. So we took the 50 years of running mean during AMOC minimum around here, and the recovery period to see the transient climate response later. So during AMOC minimum, and we also we just focus on the green line, the longer green line. So we see some warming anomalies over Greenland during AMOC minimum, but this is followed by a significant cooling along with the dissipation of the Arctic warming during recovery. And there are widespread warming anomalies simulated in the southern hemisphere, which could be an indication of a bipolar seesaw. The southern hemisphere warming is largely reduced during recovery, and there was significant cooling anomalies simulated over the subpolar regions. The precipitation changes during AMOC minimum suggest a southward shift in the main ACCESS position, with reduced precip to the north while increase to the south of the equator. So since we are interested in the climate response to a weakened AMOC in this research, the following analysis will be only using the AMOC minimum period. So we further investigate the changes in the ACCESS position in each ocean basin to a weakened AMOC. Here shows the DGF and JJA season zonal mean precipitation in the control simulation in blue line, and the AMOC minimum in this long run, and also the difference. So in the DGF season, the ACCESS strengthen and shift southward over the Atlantic and Western Pacific Ocean relative to the control. And in JJA season, the ACCESS weakens across all ocean basins and only migrates southward in the Atlantic and Eastern Pacific sectors. So now we look at the precipitation anomalies in lower latitudes in more detail in each monsoon domains to a weakened AMOC. The control is in the blue contours and AMOC minimum in red. So in the Northern Hemisphere monsoon season, both the South Asia and East Asia summer monsoon are slightly weakened with the more restricted domain. In the Southern Hemisphere monsoon season, the Indo-Australia summer monsoon is expanded and strengthened, and the South American monsoon shows a southward shift with increased precipitation over the eastern side. So finally, combining all the climate features together and just look at the Australia climate response. The surface air temperature displays a similar response to a weakened AMOC annually and in both seasons, with significant cooling over the northern part and warmer conditions to the south, and also over New Zealand. Changes in the seasonal atmospheric circulations greatly influence the precipitation patterns over in Australia. The Northern Australia precipitation is influenced by a southward shift of the main ACCESS, and thus is strengthened Indo-Australia summer monsoon in DGF. while the southern part is more sensitive to a weakening of the westerly winds in JJA season. So as a result, a significant precipitation increase over northern Australia and New Guinea is simulated in DJF, and in JJA season, a slightly weakening of the westerly wind is simulated, associated with non-significant precipitation change in southern Australia. And to also note that New Zealand displays drier conditions at all times. So basically, in summary, the 8.2 Ka event is more likely to be caused by combined effects of the lake and also the ice melting from our model simulation. And Southern Hemisphere climate displays significant changes to a weakened AMOC at 8.2 in our long and on our long 100-year duration polls, which was well. I also need to note that in previous modeling studies, they all kind of simulated a non-significant change over the southern hemisphere at 8.2. And finally, northern Australia is cooler and weather, while the southern Australia is warmer and drier, the annual mean kind of signal. And there were also some uncertainties which needs further investigation. For example, the Arctic warming simulated in our transient global climate response figure that I showed before, that leads to the fact that the Greenland temperature does not decrease significantly in our model simulation. And more analysis of the model AMOC sensitivity to different freshwater release volume, duration, and also starting from different initial AMOC strength are needed as well. So for finally, for the current runs, I've been doing the freshwater hosting experiments at 49 Ka. These experiments start from the 49 Ka control from Hamadry, and I put 0.4 spur drop at year 0 to shut down the AMOC. And basically, like after year 200, I just stopped all the fluxes to monitor the recovery. And for the second one, we kind of want to continue the shutdown. So we continue from year 200 to see the climate response after the extended shutdown. And we are also planning to do some more experiments in the next quarter. For example, to put 0.2 spur drop, etc. And yeah, that's all from me. Thank you.
Thanks very much, Yanxuan. Yeah, so we've got a bit of time for questions. I might just start by asking, do we have some clear proxy evidence of Australia? So I think maybe you said this at the beginning, but is there anything that could confirm these precipitation trends that you're finding?
No, I don't think so. I think yeah, like from here, basically they just Memorial, they kind of summarizes all the available proxies, and I think there's no over in Australia, and even though if there's one, they basically just indicate no change for this area.
It's a shame because it's not that long in the past, right? It's like I feel as though it must be possible to get something for the last 10,000 years. Anyway, thank you. Rachel, I think you're next.
Yeah, so my question is also relevant to this figure. So Antarctica is not shown, but is the event seen in the Antarctic ice cores as well as the Greenland ice cores?
I don't think so. I didn't see any like studies using the Antarctica ice cores. I guess this one is yeah, I guess because I'm not really sure, but I think maybe no. Yeah.
Yeah, just curious, that's all.
Dietmar.
Yeah, interesting study. I basically have two unrelated questions. So first of all, you mentioned your next experiment is 49K.
Yeah.
And I wonder, 49K, isn't that in the middle of an ice age with lower sea level and big ice sheets? Are you considering this, or why 49K? Or what is the condition?
And so this one is actually so Marjorie has already setting up all the boundary conditions for the 49K. I think she also presented a while ago. So I'm just taking the model from her. So she set up all the conditions already. I'm just performing the freshwater hosting experiments. Like she finished all of like the topography, the land sea and everything for the Heinrich fire.
But it looks like the AMOC is stronger in 49K. And I saw during the ice age, the AMOC is weaker. But maybe I'm not familiar with the situation, but it's the ice age. So I thought there is no AMOC or there is a weaker. I'm a bit confused.
I think the AMOC is stronger, a bit stronger than pre-industrial for the 49K.
Okay. And maybe my second question was to your previous experiments. Have you looked at El Nino? Is it changing at all? Because you have changes in the rainfall patterns. I wonder that might actually be having an influence on ENSO.
No, I haven't looked at ENSO yet. Yeah. Just basically the kind of the overall pictures at 8.2. But that would be very interesting to look at.
Laurie?
Yeah, and I just wanted to answer parts of Dietmar's question if Marjorie doesn't answer them. But basically, yeah, so you are correct. So it's marine isotope stage 3, which is during glacial time. It's not full glacial, but it's intermediate glacial. And Marjorie, with the help of David and others, set up this experiment. So with a change in the orbital parameters, greenhouse gases, land sea mask, vegetation, and also ice sheet, so including the topography of the ice sheet. And this was run for, well, we did in several steps, so now we're almost at 1,000 years or something. You are correct that in that simulation, the overturning circulation is stronger. It's much stronger than during pre-industrial, due to a combination of effects. So it's much saltier in the Arctic with much more sea ice. And there are also some atmospheric changes in the Labrador Sea due to the Laurentide ice sheet, so the bead ice sheet over North America. The overturning was probably weaker and shallower during the last glacial maximum, so 20,000 years ago. But yeah, to go back, if you want, part of the reason why we're doing 49K is because that period, marine isotope stage 3, included a lot of variation in the climate. So it was a Danskar-Oeschger variability and Heinrich variability with large changes in the overturning circulation. So basically the overturning circulation was oscillating in between a very strong state and an almost shut down state, right? So stating which state was the overturning circulation during that time, if you want an equilibrium state, it's actually almost impossible to answer. And so the reason we are doing this particular time period is because it was Heinrich event 5, which was a particularly strong event. And this is part of a project led by Russell Dresdel at the University of Melbourne, who's doing speleothem work. And he has a bunch of speleothems across Australia and New Zealand that covers this event, so 49K. So that's why we're targeting that time and not another time, so that we can compare our modeling results with this speleothem and get more insight into hydrological changes in the region. Yeah, so that's that's about it. I mean, we were obviously, I don't know, worried, concerned about the very strong AMOC. We're running imagery. It's going to start soon, the last glacial maximum, and we'll see what that gives us. And if it's as strong, we have an issue.
Yeah, Himanju just added to the chat glacial AMOC, so I guess it's the last glacial maximum. It can be very like, so that's estimates from proxies, or is it modeling? Maybe Himanju should just chip in.
Yeah, I was about to answer first, but then I saw Laurie with her hand up, so I was like, okay, she'll answer. Yeah, just to say that even the AMOC values from the proxy records are quite variable, and also the modeling simulations for LGM has given us values which are like lower than PI and higher than PI. So there's a big wide range for LGM, for which we have most of the proxy records. And yeah, we don't have any proxy records beyond that time anyway. And like Laurie mentioned, that yeah, the MIS3 is a time period of large variability. So there could be a chance of higher AMOC, but it is also true that in our simulation, because of all these topographical changes, so yeah, we are closing quite a bit of landmass from the area of Labrador Sea. So that is basically enhancing mixed layer depth in that region, and that's contributing to our higher AMOC. So yeah.
Okay, thank you, Yanxuan, and thank you for all the interesting questions.